Okay, let's start this class. And today we will talk about basic systems of these two. Actually, yeah, do you remember what we talk about? What did we talk about last class? Yeah. Yeah, but also some basic system properties, am I right? Yeah. And today we will continue to talk about some basic system properties besides those four. Okay. This is today's goal. Firstly, we will review some basic properties of systems we talk about in last class, and then we try to study the other two. Let's try to study the other two system properties and their significance. Like the first one is time invariance. The other one is linearity. Yeah. And then let's finally we will try to be able to decide the last two properties for a given system. We will try to decide if this system is a linear system or non-linear system, or if this system is time invariance or non-time invariance. Okay. Okay, let's try to review what we have already learned. We actually do you remember how many properties we talk about in last class? Yeah, it is 4, but here is 3. Did you notice which one is missing? Inverse, yeah, like inversity, like that. Yeah, because what? Because I talk about the for one system, if you want to define this is an inverse system, you need to have the original system and then try to find the inverse system for the original system. And we usually have the other two, like I talk about the transfer function to deal with this. So like for the system properties, here we mainly focus on those 3. And for the inverse systems, we will focus on later. Yeah, that makes sense to you? Okay, let's try to review. The first one, memoryless. What is memoryless? Yeah. It just depends on the present time. Yeah, like just this one, like the just try the this time input, depends on this time output. Yeah, the CT is this one and the DT. Okay, let us talk about how about this one? Is this memoryless or not? Actually, yes, it is. You just for the properties, you only find the relationship between the input and output. Other things you can ignore that. Yeah, because when the t is decided, the t plus 1 is just a value. That makes sense to you? Yeah. So this is just like the relationship between the present like signals and the present output signals. Okay. How about this one? Yeah, why? Yeah. Yeah, this is present, but this is not. Right? This is just the future time. Yeah. So this one is no. Yeah. Then let's talk about carolity. What is casual or not casual? Casual, non-casual, like casual. Yeah, depends on the present and the past. Yeah. Okay. Yeah, this one, like the past or present time depends on the output. Like signal depends on the, decide the output, and the past or the present signals decide the output. Yeah, and let's talk about this one. How about this one? Yeah, this is what this is. Yeah, because this one is equal, it's just equal this one. It's just like the limitation, like idea, right? Like for the derivative, it's just a limit idea. You just use this equation. You can see it's just depends on the present and the past signal. That makes sense to you? Okay. And then, yeah, this one is Carol. How about this one? Yeah, it's Carol. Yeah, because you can see, you just like observe this part. Yeah, just ignore this part. Yeah, this is the past time, am I right? Yeah, so it is Carol. Okay, let's check stability. What is stable? How can we decide this system is stable or not stable? Yeah. Yeah. I think you got that. Like the like a infinite input, like decide the infinite, like the bounded input, the bounded output. I'm right. Yeah, CT, DT. Okay. How about this one? Actually, this one is a system we talk about. Yeah, it is stable, like with RC circuit, like the force system. Yeah, it's just stable. And how about this one? Yeah, because since like even this one is like bounded, but you can see here the key is from negative infinite, which means there are infinite atoms will be added. Am right? The output can be unbounded, so this one is not stable. So this is like this three system is like very important. These three properties is very important properties for a system, and actually we will talk about why those three are very important for later, yeah, in the other chapter. Okay, let's talk about what is time invariance. Yeah, we also call it TI system, time invariance. Conceptually, a system is TI if the behavior and the characteristics of the system are fixed over time. Yeah, which means, for example, this is the CT system, but it is time invariance, which means your xt decide the yt, and your xt minus t now decide the yt minus t now. Yeah, this has this property, which actually I talk about the RC circuit system is a TI system, LTI system. Am I right? Yeah, you can imagine like when the t equals 0, when the t equals 1 second, and my output is a value I can write it down. When the t when my t equals 2 seconds and my output is specific 1, and then like I just stop this circuit and I will do this lab tomorrow. Yeah, again. And when my t equals 0, and the value will the value change? Will the output value change for RC circuit? Huh? The same RC circuit. Yeah, it will not change, am I right? The value will not change. The time invariant is just like talk about that thing. Like your input and output has a specific relationship. As the time pass, like you did this, you like construct the system in today or tomorrow or in the future time or in the previous time, it will not change. That makes sense to you? Yeah, this is just the idea for the time invariance, like the behavior and characteristics of the system are fixed over time, like RC system, like the force system. Am I right? Yeah. And then this is DT. It's similar thing, like the xn decides yn, the xn minus n now decides y minus n now. And then this is just like for example, the RC system. Yeah, we just talk about that. And you can see here, you're you just created this circuit. You have the specific input. You get the specific output. And then you construct build the same circle tomorrow, like the 10 days later. Yeah, you have the same output. That makes sense to you? Yeah. And then, but sometimes how can we prove this system is like a TI system? Actually, we have some steps. Yeah, usually we have 4 steps approach, like to prove this system is an IT system. The first one, we have usually we the relationship between the input and output will be given, and we can like give the input x, y, t, and then we get the output y, 1, t, and then let's try to give the other input x, 2, t. Let x2t equals this one, and then we can use the system to get y2t. Am I right? Yeah, and then we have yt like yt equation. Then we can let t equal t minus t naught and get the this equation. And get this result. And then we try to compare this one and this one. And then if this one, if those two are equal, then it is a TI. If those two doesn't equal, it is not. That makes sense to you? Because we want to, as a time pass, we want the value also like that specific output. That makes sense to you? Yeah. This is the first step, like if you want to prove if the system is TI or non-TI, this is the first step. Okay, let's check an example. For example, the sin xt, yt equal we have the relationship between the input and output, like yt equals sin xt, and then let's try to find if this one. Put this one to the equation. If we can get this equation, if we can get this value, okay, then we know like this. First, we just follow that 4 steps. We let x the input is x1t, and then our output is y1t equals x1t. That makes sense to you? Yeah, this is yeah. And then step 2, we let x2t equal x1 t minus t0, which means y2t equals x2t equals this one. Am I right? Yeah, I think this step is easy to understand. Then y1t minus y1t minus t naught, just put like a t minus t naught, just use t minus t naught, replace t. Am I right? So you can get this one. Am I right? Yeah, then let's talk about if y2t equal y1t minus t naught, is it? Yeah. Yeah. So which means which means x1t minus t naught can, if your input is x1t minus t naught, and your output should be y1t minus t naught. That makes sense to you? So which means this system is our TI system. That makes sense to you? Because we use the 4 steps to prove that. Okay, let's talk about the other example. How about this one? Yn, like what should we do? Just follow that 4 steps. I'm right. Yeah, just when I want you to, yeah, actually we have those homework. This homework, if I want you to decide if this system is a TI system, and you just follow that 4 steps. Yeah, the first one is just like x1, the first one xyn. We just give the input x1n, then we get y1n equal this one. Am I right? And then we just let x2n equal xy. Like yn minus n naught, and then we get this one. Am I right? This is y2n equal n x2n. Am I right? And then equal this one. That makes sense to you? Yeah, because we just let the x2 equal this one as an input, and y2n equal n x2n, because you just change this part, and then get this one, because x2n equal this one. Am I right? Yeah, that makes sense to you? And then let's try to, what is y1 n minus n minus n naught? Actually, y1 n minus n naught should equal this. That makes sense to you, because yn, I think this step maybe a little tricky. Yn equal n x n, then yn minus n naught, which means you just let every n minus n naught. I'm right. Here there is n. Here is n. I'm right. N minus n naught. X n minus n naught. That makes sense to you? Yeah, because you can see you let every n minus n naught. That makes sense to you? Yeah, any questions? Yeah, there is a little tricky. Yeah, because you can see here, y2n, we know y2n equal n x2n, because here, if we want to add this one, we just add y2 or x, we can now add n, am I right? Yeah, so this one equal this one. This is, I think, now difficult, but here, y1n minus, because yn equal this one, and yn also, oh yeah, maybe I just skip step. Yeah, yn equal this one, like y1n will equal n x yn, and y2n will equal n x2n. Am I right? Yeah, this is a y3n equal n x3n. Yeah, you can change this number to whatever you want. Yeah, and then you can see yn minus n naught, which means I just replace every n in this equation with n minus n naught. Am I right? So I need to replace this one, this one, this one. That makes sense to you? Yeah. Am I right? Yeah. So like this is yn. Yeah, then compare this one and this one. Is it same? Is this the same? No. So which means this system actually is now IT like a system. Okay. Then we have a conclusion. To be an IT system, the coefficient of the input xt or xn should be a constant, which means here the coefficient here should be a constant. Now, n here is a time. It is a variable. Am I right? Yeah, which means the coefficients of the input of xt or xn should be a constant, which means here should be a constant. 1, 2, 3, 4, but now n, am I right? Do you know why? Do you know why? Yeah, you can see if this is a constant, which means your input and output, just your input, your output just depends on your input. Am I right? But if there is an n, which means your output not only depends on your input, still like also depends on the time. So the time may be changed. Tomorrow time and the today's time may be different. This time at now time and the after 1 hour time, maybe it will change. That makes sense to you? So that's the reason why this, if here is a n, if here involve a time, it will now be a IT system. That makes sense to you? Yeah, am I right? Yeah. Okay, let's continue. Yeah. And then let's talk about the other one. How about this one? Yeah. What should I do if I want to tell this system is a time TI system or not TI system? What should I do? Just decide if this system TI or not TI. Step 4, am I right? 4 steps.
Yeah.
Yeah, 4 steps. Just remember that. Yeah. And then let's talk about firstly let's give this system x1t as the input, and then y1t should be this one. Am I right? Because this is kind of scaling, like a shrink, yeah. And then if our input is x2t is x1t minus 2, am I right? And then let's talk about y2t. If this is x1 t minus 2, it's just like a right shift, am I right? And then this is y2t, am I right? That makes sense to you? Yeah, because you just shrink. This one is just a shift and then shrink. This is just directly shrink. I'm right. So yeah, this is y1t and y1t. Like let's try to here we got y2t. I'm right. Let's try to like compare y1t and y1 t minus 2. Yeah. Okay. This is y2t, and this is y1t, and we need to compare y2t and y1t minus 2, am I right? So y1t is here, and y1t minus 2 is here, this one, am I right? So we need to compare this one and this one. Do they equal with each other? No, am I right? Yeah. They do. They do not equal with each other. What does that mean? To be an IT system, there should not be any scaling factor to the time variable for the input. Which means, if there is a scaling vector, this system should not be TI system. Do you know why? Yeah, actually the same reason we talk about that. Which means if you scaling your t, which means you have already deal with your time, am I right? Yeah, actually it's the same reason here. You put a time here, which means you have changed your like a time thing in the for your input, am I right? Yeah. The similar with this one, if there is a factor, which means you just shrink your time or you expand your time. Your time is now like the same time with the previous with the original. Am I right? That makes sense to you? Yeah. Okay. Let's try to do a sum. Yeah. TI property by inspection. Actually, for example, this is your like system. Yeah. This is if this there is an operator not about time. For example, it is a constant. It will not involve any time. And then if this alpha is a constant coefficient, it is not some like a time or some other thing. And this one is no scaling factor. It just equal 1. Then we can see this system is an IT system. But we know like many system does not apply this equation. Am I right? Yeah. So this method is just an easy method. If your like a system is just like that, yeah, you can quickly to tell if your system is IT or not IT. But mostly, if I ask you if your system is IT or not IT, what should you do? Just use 4 steps, yeah, to prove that. Okay, let's try to use this like IT property by inspection to tell. How about this one? If this one IT or not IT? Huh? Yeah, you can see there is an operator sin, am I right? Is there involve a time? Sin is here involve a time directly? No, am I right? Yeah. So is this a constant coefficient before x? Huh? Constant. What's like a yeah? So is there no scaling factor? Yeah. So if is this ft on if this ti or not ti? Yeah, it is. Eh? It is. I will show the answer later. Yeah, because actually, if you remember, we have already proved that. Yeah, this one. Yeah, it is like a TI system. Yeah. Okay. How about this one? Is it? Yeah, it's not because here there is an it involved time. Am I right? Yeah. So how about this one? Yeah, it has scaling factor. No, so this is not. How about this one? Huh? Yeah, it is because you can see this one just apply this rules, and this one also apply this rules. Two LTI system like minus with each other, it will LTI system. That makes sense to you because the plus minus will not change the property. Yeah, so this is yes, this is no, no, yes, yeah. But like I said, not all the system is just similar like this form. So if you want to prove, you better use those the four-step method. That makes sense to you? Okay, let's talk about the other property, linearity. Yeah, a CT and a DT system is a system that processes the important property of superposition. Do you know what is superposition? What you can remember? What can you remember? Yeah, like you can see here, like this is this is some like input, which means the if the input plus together, and then we can get the output, also can add together to get the output. Yeah, and if we give a scaling to the input, then we have the same scaling for the output. Yeah, and this is like the superposition. Okay, then combine those two, and if our system, if we have two different input and have like some scaling for the input, and then we have the output have the can add together and have the same scaling. Yeah, and then the similar thing to the DT. This is the superposition property. And if our system, which means if this system have two different input and have different scaling, and then we can get the output in this form, similar to the DT, that makes sense to you. And then we can decide our system is a linear system. Yeah, that makes sense to you. Okay, and then how to prove the linearity? Actually, we also have some steps. Yeah, 4 steps. Yeah, the first one, we consider two arbitrary input-output pairs as this one, am I right? And consider two, yeah. And then construct a linear combination of the two inputs as this one. Yeah, x3 equal ax1t plus b x2t. And then find the corresponding output, like the x3t, find the y3t, and then verify the following relationship. If the y3t equal this one, that makes sense to you. If this is this one equal this one, then we can we can prove all this as if our system input is this one and then our output is this one. That makes sense to you. Yeah. Any questions so far? Okay, let's try to check some examples. Yeah, consider a system S, whole input and output are related by this one. Yeah, this is the system called S, and this is the relationship between the input and the output. And then determine whether or not the S is linear. We consider two input-output pairs, x1t, this one, and x2t, this one. Am I right? And then to construct a linear combination of the two inputs, x3 equal ax1t plus bx2t. And then the corresponding output is y3t equal t t x 3t, and then equal t. This one, right? That makes sense to you? Yeah. And then let's talk about if y3t equal, if our like a y3t if it is equal this one, because this one is like a a y1t and b y2t, am I right? Yeah. Is it equal? Is it equal? Actually, I think this one is not difficult to tell, am I right? Oh, yeah. Yeah, equal, am I right? So which means this system is, yeah, absolutely a y1, y1t plus b y2t, am I right? So it is linear system, am I right? Okay, that's, yeah, it's linear. Let's check the other one. Consider a system S whose input and output are related by this one. And then we consider two arbitrary input as this one, this one, this one. And then let's construct a linear combination of two inputs as x3t equal a x1t plus b x2t. And then let's try to calculate y3t equal x3t and equal this one and equal this one. Yeah, I think this one. So the next step, we need to prove if y3t equal a y1t plus b y2t, am I right? Yeah, we need to decide. Yeah, what is a y1t plus a y2t? A y1t plus b y2t equal what? A x1t square power and b x2t power is equal this one, am I right? So is it equal? Is it equal? Definitely not, am I right? Yeah, one is this one and the other is this one, am I right? So yeah. Yeah. So this one is not linear. Okay, let's try to check this one. Yt equal cosine 3t xt, and let's check if this is linear. Okay, the first step, we need to construct two different inputs, am I right? Xyt, x1t, and 2x2t. And then let's try to construct input like ax1t plus bx2t, and then let's try to calculate y3t equal cosine 3t x3t. This one, am I right? Equal this one, am I right? Okay, then let's try to talk about y1t plus b y2t and a cosine 3t x1t plus b cosine 3t x2t, am I right? Yeah, this will equal this one, am I right? Is it equal? Yes, yes, it is. Sorry, yeah, you can see it is, am I right? Yeah, so this one is linear. And then let's try to expect linear. For example, this is your like function, your system. And this one is a linear operator like ax or y equal dxt, dt, xt like that. This is a linear operator, am I right? And then what about these functions? Here, this one is a linear, which means if here is a linear operator like this, and your system will be a linear system. Otherwise, it will be not. How about this one? Linear operator. Yeah, actually, this one is like a 1x, like t, am I right? Yeah, so this one, yeah, because this is a linear operator, am I right? Also, you can use this first step to prove that. Yeah, and then let's try to, how about this one? Nonlinear, yeah, absolutely. Yeah, because yeah. And how about this one? Yeah, yeah. You can see this is just like if your t is fixed, this is just a value. Am I right? Yeah. And how about this one? Also. Yes, this is also linear. You can see. Let's try to observe. You can see here the linear. Actually, you can see if your operator, if you're like deal with your like input, how change your input, yeah, as a nonlinear. For example, this one you just multiple time, am I right? Actually, this is a linear operation, am I right? But here, if you just multiple the same signal, like it is a nonlinear operation, am I right? And here you just multiple linear like function. Here also, am I right? Just you can see here for the linear, your operation, your objective is the system. You can see if you deal with your system in a on purpose way, your system is nonlinear. Am I right? The linear is just you just observe the system, the input signals. Am I right? And but the LTI, what do you focus? Actually, you mainly focus your time. Yeah, you can see from the name TI, time invariance, which means you focus on the time. Am I right? But the like a linear, you mainly focus on the like the operator. Yeah, I'm right. You mainly focus on the like signal. That makes sense to you. Yeah, your input, not the like linear, not the time. Am I right? Yeah, that makes sense to you. Yeah, so those are two different like linear like two different properties. One is time invariant. The other is like linearity. Okay, let's talk about let's to do a summarize for the all properties. Yeah, actually we how many properties we learn? How many? How many total? Five. Yeah, like actually total is six. Yeah, yeah, yeah. Like in last class we have four. Today we have two. So totally six. And let's try to review. The first one is memoryless. Yeah, what is memoryless? Yeah, just depends on the present time. Yeah, and the second one is what? Inverse, am I right? Like if this system is inverse or non-inverse, actually this one, which means you can use this system recover the original signal, am I right? Yeah, but this property we will talk about later in the specific chapter. Yeah, so here we our like exam will now focus on this property. Yeah, and the second one is the third one is what? Choral non chorality. What's that? Yeah, yeah, it depends on the present and the past. Yeah, and let me ask you a question. Is a memoryless system must be a choral system? Yeah, but a choral system now must be a yeah memoryless system. Okay, let's talk about the first one. The first one, what is it? Yes, the stability. Yeah. How can I tell this system is stable or not stable? Yeah, which means your infinite input will result infinite output, like bounded input result bounded output. Yeah, and okay. Then like you need to yeah this one there is no like specific you need to check if your input bounded input result bounded output. And then let's talk about the two properties we learned in today. The first one is time T time yeah Ti time invariance, yeah, which means time with the system will not change as the time pass like that. Yes, it's the same system. You check it today or tomorrow or in the future time, it always give you the same output like that. Yeah, yeah. And then if you want to tell the system is Ti or not Ti, you can use these rules, but not all the system can use these rules. What method you should use? Yeah, 4 steps. Yeah, you need to check, try to construct those things and to compare y2t if it is equal y1t minus now y1t, just y1t after deal with y1t. Yeah, and then for the last one is that's a property.
Oh,
yeah, linearity. Yeah, and if for the linearity, which means I missed one. For the let's talk about this firstly. For the linearity, and there is some rules, and if the operator here is a linear operator, yeah, it's not like the power, like the square or something like a. You can see here. Actually, I just missed here. Sin exponential square or power is not linear. You know that, am I right? So if you see this is not a linear system. Yeah, and you can, but not all the systems apply to can use this rule. Yeah, these 4 steps. Yeah, you need to like use those 4 steps to try to verify if this system is linear or not linear. Okay, and then. Okay, let me try to point out one very important thing. Like I said, for the Ti property, you mainly focus time. Am I right? Yeah. If you change the time for in the system, am I right? But the linear is just you focus on the signal. Yeah, if your signal is you like change like in a nonlinear way or some improper way, yeah, your system is nonlinear. Yeah, that makes sense to you. Okay, yeah, this is all the properties we talk about, and then this is a cost roadmap. We have already finished chapter 1, signals and system, and then next Monday I will do a review for the chapter 1. And we're supposed to have an exam on Wednesday, but we can have it on Friday since Honey have something to do with. And then, but on Wednesday, I will talk about LTI system. Yeah. And okay, this is today's class. And this is all the homework for chapter 1. Yeah. And any questions so far? Okay. Yeah. And yeah, I will tell you what we will have in midterm 1. Yeah, next class. And you also can have a cheat sheet. Yeah. Okay. So far so good?
Yeah.
Okay. Yeah. Hi, honey. I didn't see you. Wait. Oh.
It was dark, so I just went through.
Oh, I didn't see you also. Okay. Yeah. Hi, honey.
Hey.
I just saw you. Yeah. So did you yeah get everything I talked in today's class?
Yeah. I was here the whole time.
Okay. And yeah, Christian has already allowed us to have the has agree we have the exam on Friday. I think yeah, you told me like Matthew also agree. I'm right.
Yes, I did. Yeah.
Okay. Yeah. Did you check the video, the last class video?
Yeah. That's why I emailed you because you said in the last video that it was gonna get moved to Wednesday.
Yeah.
Because as I was watching it, I was like, oh, I can't do that date. Yeah, I saw it.
Okay. Yeah. Did you see this is all the homework for the like
I saw
chapter
it.
1. Yeah. Any questions so far?
No, ma'am.
Well, okay, that's great. Any question, problem, just let me know. Yeah.
Okay, thank you.
No problem. Yeah.
All right.
Okay, we will have a review for chapter 1 on next Monday. Yeah.
Okay, bet.
Okay.
All right.
Okay.
Thank
thanks.
you. Bye.